let's look at mutual inductance and self-inductance. So here we have a setup with two different solenoids, and this is the primary solenoid, and we call it the primary because it is connected to an AC power supply, so it has current going through it. And here we have a direction drawn for the current, but since this is an alternating current, that direction changes very frequently. So this is just the direction at one point in time. Now, this second solenoid doesn't have any current going through it. It is just connected to a voltmeter. So we'll call this the secondary. Again, the primary is the one that has current going through it at the beginning, and then the secondary does not have current going through it. But the thing is that a solenoid that has current flowing through it will produce a magnetic field inside the solenoid. So these red lines here are the magnetic field lines. Now, since the direction of the current changes constantly, the direction of the magnetic field will change constantly. So essentially, we have this secondary solenoid here that has magnetic fields going through it in either to the right or to the left. It just keeps alternating, and when that happens, the secondary will react. So the changing current in the primary will induce an EMF in the secondary by Faraday's law. So the direction of the magnetic field is changing here. It's going to the right or to the left, alternating, and the change in the magnetic field will produce a changing magnetic flux through the secondary, and that changing magnetic flux is going to induce an EMF in the secondary. The reason we know that is because the voltmeter here will record this EMF that will be produced by this secondary. So what we know is that the magnetic flux times the number of turns is going to be proportional to the current in the primary. So the magnetic flux through the secondary times the number of turns is proportional to the primary current. That proportionality constant is M, and M is what we call mutual inductance. That means that from this equation, M is going to be number of turns in the secondary times the flux through the secondary divided by the current in the primary. That's what we have here. And mutual inductance is measured in henries. Now, if we want to rewrite Faraday's law in terms of the mutual inductance, starting out with Faraday's law, EMF is the negative of the number of turns times the change in the magnetic flux with respect to time. So that would be number of turns in the secondary times the change in flux in the secondary with respect to time. And if we now take the number of turns and put it inside the delta symbol, then we end up with negative delta times this quantity with respect to delta t. And we saw that this quantity over here is the mutual inductance times the current in the primary. So then the EMF is negative delta MIP with respect to time, but the mutual inductance doesn't change. What changes is the current, so we can take the M out and end up with negative mutual inductance change of the current in the primary with respect to time. So then Faraday's law in terms of mutual inductance is going to be negative mutual inductance times change in the current in the primary with respect to time. Now, we've been looking at a magnetic field through the secondary that was caused by an external device here. So we had a device creating a magnetic field that was changing, and the secondary experienced that magnetic field. But that is not necessary. We can just have a magnetic field in solenoid, and when that magnetic field changes, then it will create a reaction in this solenoid, and that reaction is called the self-inductance. So now we know that the number of turns in this device times the magnetic flux is proportional to the current that is changing through here. That proportionality constant is the self-inductance, so then we have number of turns times the magnetic flux is equal to the self-inductance times the current through there. So then self-inductance is number of turns times flux divided by the current. And if we apply the same derivation that we had over here, we end up with the EMF in here being induced is the negative of the self-inductance times the change in the current with respect to time. And we call this self-inductance usually just inductance. So we don't use self-inductance very much, but in this lecture, just to differentiate it from the mutual inductance where we had two different devices, one causing the second one to produce an EMF. Here we don't have that, so we'll just call it the inductance.